I want to be a good developer. And I'm assuming that if you're here, you also aspire to be good developers. Who wants to be a good developer? Raise your hand. Wow, everyone. Who would be satisfied being an average developer? Yeah, a few hands, right. Just for the sake of checking, who is actively pursuing the goal of being a bad developer? Yeah, a few hands.
Define bad.
Yeah, so what's good, what's bad when it comes to being a developer? So if we take that to the beginning, our job as developers is to produce software, and to craft software, we write code, right? So what follows out of this is that good developers can write good code, right? It sounds good. Now, if you think about it, think back, for example, at your last day at work before coming to the conference. Did you spend your whole day writing new code and pushing it to the repo? Probably not. No, there's something else that we do with code, apart from writing it, and that would be reading it. Yeah. So, good developers can write good code and read good code, right? That sounds good, has a nice sound. Now, I don't doubt that your code is absolutely perfect, but perhaps you've come across some code that wasn't as perfect as you would like it to be, right? So if we come across it, then it means we have to deal with it. So in our job, we also have to work with OK code, and with code that's not that good, perhaps, and with code that's really not good. The point of the matter is, we have to work with the code we get to work with. And I think that participates to what's being a good developer. For those of you that don't know, I've spent the past years of my life working on those two aspects. My name's Jonathan Boccara. I write on the blog Fluency++, which is fluencypp.com, which is about writing good code mainly. And I've just written a book about working with existing code, what we could mainly call legacy code. So the book is called Legacy Code Programmer's Toolbox. And I work at Murex. So today, we're going to talk about how to work with existing codes, and in particular, how to understand existing code. We're going to go through 10 techniques to understand existing code. Some of those techniques you might know, some you might discover, some are classical, some are, I think, new, some come from software development, some come from other fields. And some of them are more heuristics than actual algorithms. But anyway, all in all, these are my favorite 10 techniques that I use every day, and there are probably more of them. And the outline we're going to follow is first having a global overview of a code base, like locating where is what, with 3 techniques. And at some point, we're going to have to read code. And we're going to see how to be a code speed reader, like to make sense of code really quickly. 4 techniques. And then we'll see how to understand the details, the intricacies of a piece of code whenever we need to do that, even if it's not that often. All right? So let's start. Let's start with technique number 1, which is know your I/O frameworks. To understand what that means, let's take an example. So we have our app. Yeah, there's an inviting compute button on it, and the user can click on the button, and the answer is 42. I'm not sure what the question was, but the answer is 42. Now, this animation went extremely fast. We're going to see it again in slow motion, right? Let's do that again. So the user brings the mouse over, clicks on the button, we go through a purple wormhole that drives us to the code. So the user clicks on the button, we go through the purple wormhole, and we get to one specific place in the code that works out the result, which is 42, and this 42 gets pulled up back to the UI and gets displayed. And through that purple wormhole, we managed to reach one specific place, the right place in the code that can be in a position amongst tens of thousands or hundreds of thousands of millions of lines of code. And this is the UI framework, right? If you have a UI framework, this is really not rocket science. The point is to get familiar with the code of that framework. So in practice, this technique consists in blocking off a few hours of your time and trying to follow everything that happens from the moment you click on that button, the moment the event is generated, all the way to the business code that actually makes the functional computation. It's going to be a bit tough the first time, but the point is to try to find your way around so that the next time you're looking for something, that you know where to put your breakpoints in the UI code and directly get to the business code. This saved me literally, I think, hundreds of hours of research. Now, the UI framework is just one specific case. What if your app doesn't have UI at all? Perhaps it's a service, and then your interface, what you're seeing, is a REST handler. Or perhaps what you're seeing is logs. Or perhaps what you're seeing is unit tests. All of those are I/O in the general sense, in that they are the purple wormhole that can drive us to the code we're looking for. And this is what we see as humans. Assuming that we developers are humans, which is a completely different discussion we're not going to talk about today. But this is what we see, and this is what separates us from the code. And knowing how to navigate through the purple wormhole of the UI, the I/O framework, is a priceless help to locate anything in the code that corresponds to something in the interface, in the general sense. Now, assuming that you can navigate that purple wormhole, what are you going to look for? One thing you can look for is technique number 2, is looking for a stronghold. So I'm not a native English speaker, and I learned that word, stronghold, in Game of Thrones. So in Game of Thrones, a stronghold, it's a small castle where a family lives. It's their base, it's their home, that's their safe place they know perfectly well. And they start from that place to explore the world, or conquer, or make alliances, or whatever, right? Now, what's going to be displayed is the mental representation of somebody who starts on a new code base. Sorry, I forgot to put up the legend. So when you start on a new project or a new job, this is your mental map, right? Every pixel here is a piece of code that you don't understand, right? Because you don't know anything about it. Do you remember those games we used to play when we were kids? I'm not sure, I don't know if they're still around. Where you start with a base and there's a wall fog. And the more you walk around and the more you unveil on the map, like Age of Empire style, I think they're a great analogy for a code base. In that sense, that the map is like the code base. the stronghold, the small castle, is a place in the code that you master, something you understand perfectly well. And it doesn't have to be big. It can be just down to one line of code, for example. And if you can understand that line of code, if you can map it to something in the application that you understand, then probably you can make sense of the line which is just after it and the one before it. And if you understand those three lines, then chances are you can also understand the line after it and the one before it. And before you know it, you know 5 lines of code perfectly well. And when you know that chunk of code, if you look at the code that invokes it, then you can relate it and perhaps understand what it's doing, and things start clinking into place. So what can be a stronghold? An infinite amount of things that can be a good stronghold. We're going to see one example. So one time I was working on that project that involved computations, and there was this thing which is a linear interpolation. So linear interpolation is when you know how x0 maps to y0 and how x1 maps to y1, and you have this new x, and you'd like to know which y maps to x. And to do that, we assume there's a proportional relationship between y and x, and you can deduce y based on everything else. I'm perfectly comfortable with that. This is basic maths. And so I was using this application where I knew this would happen in a specific use case. And when you know that kind of thing, you can go through the purple wormhole in the use case to the corresponding code and try and look for that, right? And ignore everything you don't really understand. Just try to follow what looks like it's going to lead you to that linear interpolation. Assuming a linear interpolation is a stronghold, that gives you a new stronghold when you found it, right? And from that new point, you can start exploring the surrounding code and being more and more familiar with more and more code. So that's technique number 2. Find a stronghold or several strongholds and explore the code from them. Now, this is a local analysis. And if you need to understand several hundred thousands of lines of code, it's going to take a while. So it's also interesting to take a step back and see more code, or at least reach out farther in the code base at the same time. To do that, there's technique number 3, which is to analyze call stacks. So I'm assuming everyone is familiar with a call stack. Does anyone want me to summarize what a call stack is? Right. So what's interesting, what's instructive in a call stack is that it shows several modules where the functions belong, right? And this gives you a screenshot of the communication between several modules in your application. And you can follow along, see what's going on. Going back to the map analogy, the call stack spreads farther on the map. And this one looks like an interesting call stack because it spans across several regions or countries, a bit like spanning across several modules. Right, so this one is an interesting call stack. Now, not all call stacks are interesting. Like, for example, that one, not really interesting. Right, doesn't reveal anything in the code. So, what makes a good call stack in the sense of learning the code? I think there are 2 characteristics in an instructor call stack. One is it has to be deep, because the deeper and the more info it shows, right? That makes sense. But what's more, I think it has to be in a representative use case of the application, right? So that you see what the application is made around. Right, now, how do we find them? Like, imagine you're getting this new project and you'd like to see an interesting screenshot of of a call stack. How do you find it, right? Well, if you know someone who knows, you can always ask them, which is a bit obvious. But on the other way around, if you are in charge of training somebody who's new in the team, I think it's a great thing to spend time on. I often do that with the people of my team. I often sit with them and I choose a call stack and I show them, and we study the various stages on that stack to see how the app is structured. Or you can ask what's a common use case to whoever knows, perhaps the people that use the application or the business people in your company, or perhaps resort to the documentation. And once you've identified what's a representative use case, then find the code by going through the purple wormhole. There's also a way to see several call stacks at the same time, which is called flame graphs. So a flame graph is something like this. So you see several call stacks at the same time. There are various sorts of flame graphs. Some of them batch up stacks together, even if they don't happen at the same time, so that we show where performance is going. Some of them show them in the order of their appearances. Right, this closes off the first part of exploring the code. So we have 3 techniques. Know your I/O frameworks, find a stronghold or separate strongholds, and analyze call stacks. Right, let's move on to part 2, which is about reading code. So the term speed reading comes from not from code, like from reading books and text in general. And I think there are a lot of things to draw from how to read anything quickly and use it to read code quickly, right? So we're going to consider code a bit like prose. A bit like if it was a book, and we'd like to read this book in as little time as possible, right? So let's dive in. There's this book that's been popular for perhaps a century or something. It's called How to Read a Book, and that's about how to read a book, essentially. And so I've read that book, and it says a lot of things. It's a good read. And some of them I think are really interesting is that when you read a book, a non-fiction book, don't read it cover to cover, right? What you read cover to cover is fiction. So, and for code, I think that it looks like non-fiction. Unless you read code on a Sunday evening in a comfortable chair next to the fireplace in your winter house in Normandy. In which case, you probably want to read it line by line. But when you're at work, you want to go quickly, and it really looks like non-fiction, right? So you don't read a book cover to cover, and you don't read code line by line. Also, in a book, in a non-fiction book, the goal is not to understand every last thing. And I think that's the same for code. When you read a piece of code, the goal is not always to understand everything. And finally, there are places that are richer in terms of information, that are more dense than others, in books and in code as well. So one way to mix all those 3 guidelines together is to look for where the information is and focus on those places and ignore the rest. Right, so this is what we're going to see on the next 4 techniques. It's where the information is in code. That leads us to technique number 4. Start reading from the end. So it turns out that in a book, and I think in code as well, the information tends to be at the beginning and the end, like the beginning of the book and the end of the book, there's a summary. And it's also true at the beginning of a chapter and in the end of a chapter. And it even comes down to the beginning of a paragraph and the end of a paragraph. And the middle is like detail. So in the beginning, say, of a function, for example, it's the prototype. That makes sense. And that's something that we read anyway. The point is to read the end of a function. Now, what's the end of a function? Well, yeah, let's see an example. I'm going to show you some codes. We're going to go briefly over an example for each technique. And at the end of the 4 techniques, we spend more time in a chunk of code in order to mix them together and understand it better. All right? So this is a piece of code that's not particularly good or bad, in my opinion. It just comes from the internet, an open source project that I didn't know from before. It's just there to support the examples. Right, so what's the end of the code? The last line of that function is a return statement, right? So it says return alignments. At this point, we don't know what alignments means, but it must be something very important. Because the whole life purpose of that function is to return alignments, right? And even if you only look to that single last line, you know the purpose of that function. And perhaps this is enough. Perhaps you came here because this function is called from somewhere and you didn't know what it was doing, and knowing it returns alignment is enough, right? But let's assume that you'd like to know more about about the body of that function, right? So if alignments is so important, then let's see what's happening with alignments. So what we can see is alignments is filled from block, whatever block means. So block must be somehow important as well. Block is filled from reader, which is filled from IS, right? With this analysis, we have a glimpse of the structure of the second half of the function. And it took just a few seconds, right? So this is the kind of things we can learn from reading from the end of a function. Now, in a function, the end is it's a word that doesn't really fit. I think the end of a function is more like the outputs of the function, the purpose of a function. Now, what can be the output of a function? Well, it can be a return value, like in this example. But it can be other things, like, for example, an out parameter, like, non-const reference that the function has to fill. Or it can be a data member if it's not a free function, but a method. It can be I/O, like the function is displaying something. Or it can change a global variable, for example. Or, and I apologize in advance for what's going to be displayed. If you're a sensitive person, perhaps you should look away. I'm not saying this is good, but if it's happening, then it counts as an output, and this is something you should look for. Now, I'm not saying you can find those guys 100% of the time, like particularly global variables, for example. If it's in a function that's called in your function and that's like several layers down the stack, perhaps you can't see it, but most of the time you can see those guys, particularly those up the list. And anyway, in all cases, I think that's what we need to look for first. And even though they can be, in theory, anywhere in the function, I think that most of the time they're towards the end, right? Because the function, the bulk of the function is there for that purpose, so it has to be executed before that purpose. So the purpose is probably lingering towards the end. Right, so that's one place where the information is. There are other places, like in technique number 5, for example, information is in the frequent words. So by frequent, I mean literally the number of occurrences of a given word. And if a word or term appears a lot in a piece of code, that it means it must be important, right? Let's see an example. So again, chunk of code coming from the internet, which is too long to fit on a slide and be readable. But we don't read code line by line, so it doesn't matter. we're going to run a word count on that chunk of code, on that function. And this is what comes out. So I'll show you after how to get a word count quickly. Now, we see that amongst the top words, there's this one, value, which, if we highlight it, happens to be about everywhere in the function. Right, so it must be something that's important at the scale of the function. And indeed, in that particular function, it fills value. Right. Now, if you contrast this kind of analysis with reading line by line, how much time do you need to figure out that value is important if you read line by line? Right, you probably need to read like half of the function or even more to realize that. And this takes a few seconds. Another interesting thing to see in the word count is the inputs of the function, the parameters. If they are, like in this case, in the top words, they're in the top words. In this word count, it's truncated and goes all the way down. So these guys are really the top, the most frequently occurring words. In this case, if we highlight them, there's a pattern that draws. And it's interesting because they always go together. And if we read their code, which we won't do here, we can see how they relate together, and perhaps we can make them into one object or something. Now, this is not for saying that it's always the case. Like in this code, for example, there's this parameter that's not in the top frequent words. There's another interesting measure on the top of the sheer amount of occurrences. It's the span. So by span, I mean the distance in lines of code between the first occurrence of a term and the last occurrence of a term, right? And for example, items, the first occurrence of items is 44 lines before the last occurrence of items. Now, 44 doesn't mean much if we don't know the whole length of the function, right? So what's perhaps more interesting is the proportion this is taking in a function. So the proportion is the span divided by the length of the function in lines of code. In this analysis, there's a pattern. I don't know if you can see it, but the third one, token, is amongst the most frequently occurring words and has a quite low proportion, right? What does that mean? That means that it's used intensively in a local part of the function. And indeed, if we highlight where token is used, it's only in this block up there, and that's information. Right, this is information about this block. This block is really focused around token. Perhaps it reads from token, perhaps it fills token, and perhaps this block is one responsibility in the function. And what follows out of that is perhaps we should take it out in a sub-function, for example, and make this function shorter and clearer and more with a better cohesion. So word count helps reading the code, and this is our purpose today, but it also helps give refactoring ideas. Now, how do you perform a word count? There's a tool that we all have in that room. It's a pair of eyes, which means that if you only have like a couple of lines of code, you don't need a tool to run your word count. You can make a mental word count and seeing what's occurring frequently. Now, the second most simple tool is the IDE. Like if you press, I don't know, star on Vim, for example, then it will highlight that particular word. Or if you have like a big chunk of code that doesn't fit on your screen, then you can use a dedicated tool. I couldn't find one, really, so I made one. It's available online on Fluent C++. It's on fluentcpp.com/word-count. Just paste in your code, press run, and you get this kind of analysis with occurrences and span. Now, several ways to count words. One is counting words, which is what we did. One is chunk up the camel case symbols into individual words, so that if a concept is present in different terms, then it can accumulate in your word count analysis. It can also be sensitive or not to the case. We've seen how to count words on a function, but we can count words on larger scales, like, for example, on files. Right? So if you have this huge file and you have no idea what it's about because it doesn't have a proper name, then you can throw it through the word count tool, and it will show you who are the main characters in your file, and that will give you some indication about what this file is about, and this is really helpful. And if anything, that can bring up questions. Like, I see these terms is occurring all the time. What does that mean? That's something like a new person in the team can ask, for example. Or if you get into a new project, that's something you can ask. Right. Now, another place where the information is, it's on control flow. So back to this book, the How to Read a Book. It says that you should spend a lot of time in the table of contents when you start with that book, right? Because it will show you what the book is about, really, what it's going to talk about. And sometimes you're going to stop there because you're going to realize that this book is not for you. It doesn't answer your problem, right? Now, going back to code, what's a table of contents? Well, there's, I think, a very approximate, very rough table of contents we can get out of a piece of code. It's the control flow. By control flow, I mean those lines that contain if, else, while, do, and so on and so forth. This structure function, right? So if we could just see those lines, we could see the structure of the function. We wouldn't see what the function does, but we would see what are the topics of that function. And if it's a long function, it goes much faster than scrolling all the way down. So in practice, you've got some code. You run it through something that will filter the line. So this is a Vim command. Sorry if you don't like Vim. I'm sure all IDEs have also that kind of command, don't they? And then that filters the code and only leaves those lines that have an if or for, else, or whatever. So this output is much shorter, right, than the previous one. So in theory, it's easier to analyze. Now, I've chosen this particular example on purpose because the output is not readable. Sometimes it is, sometimes, like in this case, it's not. Now, if it's not, then this is code, and you can apply other techniques on this code, like a word count, for example. Right? And if we run a word count on that filtered output, and it shows that C setting seems to be an important thing, and if we look at what's going on with C setting, we see that it's tested against a type. So this function looks like it's trying different type to test a setting. Right, so that's the first indication. We're not going to go further in that example because we're going to spend more time in another example. If you want to, if you don't have Vim and you'd like to filter on control flow, no, I'm joking. I'm sure you have something in Emacs as well. I don't have anything against Emacs. Anyway, there's this online tool as well. So fluentcpu.com/control-flow-filter. Paste in your code, press run, and you get your filtered output. Right. So this brings us to the last technique of becoming a speed reader of code, which is scanning for the main action. Are you familiar with that principle that's called the 80-20 rule? Right. That's something that seems to be I don't know, like in the law of nature or something. I think it originated in economics, where it says that 20% of the people seem to have 80% of their wealth, right? And this proportion seems to be general, and that in general, 20% of the causes are responsible for 80% of the consequences. And some even go as far as saying it's a 90-10 principle. In programming, we use this extensively when it comes to performance, right? When we say we should start by writing clear code and measure afterwards if it's fast, and if it's not, then it's probably a local bottleneck that we can fix, because 10% of the code is responsible for 90% of the time, right? The execution time, right? So this is the principle. Now, I think this applies quite well for code, not in terms of performance, but in terms of meaning. As in, if you have a chunk of code, function, for example, I think that a lot of lines don't have a lot of meaning. I don't know if it's 10 or 20 or 30 or whatever, but there are certainly lines that you don't care about. They have to be there for the code to compile and stuff, but you don't really care about when you want to understand what the code is about. So, technique number 7 is about scanning the code and searching for the main action, right? The main action being the lines of code that contain the most meaning. So, it's a fast operation, right? It's a scan. So you check line after line, but you don't actually try to understand it. You just decide, is it the main action or not, right? And what matters is not to get it right all the time, it's to go quickly. Because you can, if you're wrong, it's okay, because you can always go back to the code. So how do we decide if it's the main action or not? Some heuristic here, like intermediary variables, probably not the main action. Special cases or error cases, not the main action, not something you care about when you try to discover what the code is about. Anything complicated, I mean, if it's an 80-20 rule, then it has 80% chance of not being important, so just move on. Right, now we're going to see an example where we're going to combine all four techniques, looking at the end, counting words, filtering on control flow, and scanning for the main action, and we're going to try to understand a piece of code that we don't know. All right? So this is the code. It comes from the internet, open source project, which is about genetics, as far as I can tell. So let's start with the first. Don't read it line by line. Let's start with the first technique. Let's look at the end, right down there. So down there, we see that we are adding something to positions, and then we're sorting positions. Therefore, positions must be something important in that function. If we look a bit above, we see that position is connected to something that's called insertion map. And we see that this map seems to be filled a bit up above, and positions also seems to be filled above. So this definitely looks like something important. Let's make a word count. Right. So the term that occurs the most frequently is CHR. Let's highlight it. CHR happens so at the top of the function. It's a parameter, but it's only on the first half of the function, right? So the first half of the function seems to be drawing information from CHR. And we can see that it's, if we highlight the second most frequently occurring word, which is insertion map, it's all the way through, so it really looks like something important, and it's connected to CHR, so it's...
We can guarantee that it's not discarded.
That wasn't me. Right. So insertion map seems to be something important. The second one is block. Yeah, and the one after, the one, yeah, they are equal, block and positions. Positions, we already saw it, it's important, it's all the way through, it's connected to CHR, so it's definitely something important. So this function seems to be drawing information from CHR and fills insertion map and positions. Right. Now, let's filter on control flow. So this is the output of the filter. So this, we can see that we still see appearing insertion map positions. So they are in central positions in the structure of the function. And most of the structure is this for loop, right? So there's simple code before the for loop, and then there's this for loop with a lot of control flow in it. So the for loop is probably where the main complex things are happening. Okay. Okay, now final technique, we're going to scan for the main action, and we're going to do that together. Okay, so raise your hand if you think that this first line is part of the main action. Nobody. Okay. Let's do the same thing for this line. Who thinks it's the main action? Right. This line. Okay. This line. Yeah, looks like an error case. This line. Right. Did you get the point of the game? Right. This guy. This line. Right. This line. Error AI. Okay. That one. Right. That one. Okay. Oops, sorry. This one. This one. This one. That one. I have no idea what Sam hide small indel means, but it has an 80% chance of not being important. That one. Okay. That one.
Well, I would say anything that touches position map and insertion map seems like a global variable.
All right. Just for that line, who thinks it's in the main action? Yeah, a few hands rising. Okay, let's keep it in the main action. That one, that initializes blocks. Okay. That one. That one. Okay, let's keep it. This one. This one. This one. That one. Oh, sorry. Let's do that. Sorry, this one again, because I. Okay, a few hands. Let's keep it. Right, this one. The if statement. The if clause. Right. That one. Quite a few hands. Let's keep it. This one. Yeah. This one, positions.add. Okay, all right. Else. This one. Yeah, all right, let's keep it. Sorry. That one. Okay. And finally, this one. So, yeah. Okay. Right.
Have these problems, and
perhaps I should let them do that talk. Right, so first observation, seems to be consistent with what we said before. In particular, that the action was, we said that it was probably toward the end of the function, and this is what it's looking like from our analysis. And the lines that contain the main action contains the main characters, positions, insertion map, and so on. Right. For this specific function, so it's about a genetic project, and I think that CHR means chromosome, and alignments is when you compare the same chromosome amongst different species, and you see where they differ and when they're the same. And I think this function goes through the various blocks, which are chunks of DNA, and adds them to position by seeing where they start and how long they are, and they concatenate them if they knew it from before. Right. So this was code we didn't know, and we now have a fair idea of what that means after a few minutes. I'm sure that if we worked on that project, and if I knew a bit more about genetics, that would make even more sense even more quickly. But that's the point of those 4 techniques to make sense of code quickly. Okay, so the 4 techniques are start reading from the end, find the frequent words, filter on control flow, and scan for the main action. This brings us to the last part of this presentation, which is about understanding the details of code. Now, before we get into the actual techniques, this is not something we should do often. Right? I think that most of the time we just want to get an approximate information about what this code is doing, what is it about. And in some cases, when we want to, I don't know, fix a bug or to make a refactoring something, then we are concerned about what it's doing exactly in its intricacies. So technique number 8 now is to change the code in order to understand it. This is about refactoring, and this is one specific type of refactoring, which is about decoupling. Let's see an example. Let's say we have this order class, which is a massive class that has dozens of data members and dozens of member functions, and that scares everyone, and no one knows everything about order, and it's been there for 10 years. Ryan, sounds familiar? And amongst the member function of order, there's process, whatever that means. That calls a lot of things, and including process taxes, which seems to be about taxes, even though it doesn't say exactly what it does with taxes. Let's say that we want to understand process taxes, want to know what it does, and we want to clarify the code that's around that function, that member function. Let's see the code of process taxes. Just a handful of lines of code. It's funny how just 6 lines of code can take more than 6 seconds to pass, isn't it? So process taxes uses some data members. They are the variables that ends with an underscore. They're down there. Price, total price, origin country, destination country. So we're going to try to decouple process taxes from order, right? And this will help us understand better what process taxes is about, and what some of those members are about, like total price. What's total price? How is it different from price? Okay, let's start. As a first step, we're going to stop using the data members from order, right? We're going to use getters and setters. Now, I'm not saying that getters and setters are a good thing. Perhaps they are, perhaps they're not. It's not the purpose of today. But let's assume that we have getters and setters, or we make them temporarily just for the purpose of that refactoring. And now the compiler can show you where you forgot to replace getters and setters, because process taxes is now a free function, right? So it doesn't have access to the data members. This shows us what are the inputs and the outputs of this process taxes function, right? The getters show the inputs and the setters show the outputs. So it has 4 inputs: price, origin country, destination country, and total price. And it has 1 output, total price. Right, let's refactor this function further by passing the inputs and the outputs. And now it's completely separate from order. We don't see anything related to the order class anymore in this code. Now, when we do that, it turns out that total price, which was supposed to be an input, is in fact set here and used here as an input. So it's not really an input. It's just it was conveniently writing into the data member as an intermediary variable. So total price is not an input. It's just an output. Now, we can understand better what this code was doing. It's returning total price after making some tax-related processing from the price and the countries. So likely, the total price is the price after taxes, and this function is computing the price after taxes. Then we can rename total price, right? Price after taxes, which makes more sense, right? And now we understand much better how process taxes is related to the rest of order and what it's doing. Now, this talk is about understanding code and not about refactoring, but this is a way to understand code that you don't have to keep. This is what some people, I think it's Michael Feathers that coined the term, scratch refactoring, which is a refactoring that you make quickly and then you throw away afterwards. And in our case, this refactoring helped us understand what the code was doing. Now, perhaps this one was good to keep, and I think it probably was, but it's not really the point. There are other refactoring as well, like renaming, for example. If you consider that being a refactoring, that's tremendously useful to understand code. If you figure out one particular object, what it means, and you rename it, and then the code looks much clearer afterwards. Which brings us to technique number 9, in which we're not going to spend a lot of time, because it's about you finding that in your code base. It's about finding practice functions. So what do I call practice functions? It is a function that is adapted to analyze the codes. It has to be complex enough to be challenging so that it's good practice, and more importantly, not have any dependencies on other functions, or very limited ones. So that if you understand that code, you are in a safe place. You can't get lost, right? Because if you try to understand a piece of code that has a lot of dependencies, then you're going to go through those dependencies to see what they are about, and so on and so forth, and it can take forever and be really frustrating. In this kind of function, you're in a local place, even if it's large and complex, and that's the challenge. So perhaps take a moment to think about in your code base what you would consider being practice functions, and try to practice your skills. Or if you're in charge of training people, send them in those functions to practice their code understanding skills. All this leads us to the last technique of today, technique number 10. Associate with other humans. Again, assuming that we developers are humans, which is really not the topic of today. Before actually getting into this technique, let me give you a disclaimer. There are about as many ways to work as there are developers, and when it comes to teaming up, there is, I think, the square of the amount of developers, because it works in pair, of ways to work. So this is not the Bible, right? This is just my favorite way of teaming up with people, which you can perhaps get inspired from and adapt in your case, right? But if you work differently, then that's perfectly okay. So why teaming up in the first place? There's the practice of pair programming, which is quite widespread in our industry, and it's a great thing. But something that's much less widespread is pair understanding. It's not even a word, right? So that consists in you trying to understand code and failing to understand that piece of code and asking for somebody else to sit next to you and look at the code and try to understand it together. Why is it a good thing? Well, first thing, it's a new, fresh look from the other person. And at some point, when you get diminishing returns from your efforts, then you get higher returns by including the other person, right? Now, you've probably heard about the technique of rubber ducking, which consists in explaining your problems, or rather explaining what you know about your problems to a rubber duck, rubber duck, boss thing. And the fact of explaining it, even if the rubber duck doesn't answer, makes you realize things you didn't when you were in your bubble, right? So this is more than rubber ducking. This is humaning. And that works at least as well as with the rubber duck. Also, perhaps this other person, they just know that piece of code, or they will recognize a pattern, or know something you don't know, and you'll pull your knowledge together. And it's also easier to avoid distractions when you're with somebody, right? Now, to be even more productive, I think that it's even better if the other person has already tried to understand the code, so that you're not both of you trying to scroll up and down at the same time on your screen. But I think that is still worth a fresh look, even if the person doesn't know the code. Right, this closes off the third part about understanding, focusing on the details of a piece of code. And the three techniques in that part are decouple the code to understand it, identify practice functions, and team up with other humans. This closes off this presentation. It's about 10 techniques to understand code you don't know. So the 10 techniques are: know your IO frameworks, find your stronghold, analyze call stacks, start reading from the outputs, count words, filter on control flow, scan for the main action, decouple the code, identify practice function, and team up. This is about understanding code, and if you'd like to read more about working with existing code, you can check out this book, which is exactly about working with existing code, Legacy Code Programmer's Toolbox, which is available on the internet on leanpub.com/legacycode for the ebook, which is available here tomorrow at the conservatory at lunchtime, where we'll be signing books along with 3 other authors, so you can get paper copy. This was 10 techniques to understand code you don't know. Thank you so much for being here.